that we've had a chance to take a look at Euler's method and see kind of how it works, and we have a sense of the error that can accumulate as we take steps, it's helpful to kind of visualize what's going on. And so what we have here is a picture of the slope field for our differential equation. And if we started here at our initial condition of 0, -3, this curve right here, you can see, kind of obeys the slope field completely. And so what you're seeing on this curve right here is the actual solution curve, as opposed to what we just got done calculating, which was kind of a step-by-step process of starting at the initial condition, reading the direction that the direction field is telling us to go, taking a step, and then reading the direction from there, taking another step, reading the direction, and then taking another step. And we wound up going out 3 steps, 3 single unit steps. And this is our approximate location. So this right here, that's our approximate solution curve. Now, it's not much of a curve because, of course, let me scoot this up. It's not much of a curve because, of course, this thing is just a series of little line segments. But for us, as calculus students, we recognize that if you have small enough line segments, then they start looking like a curve, right? So what we're visualizing here, what we're trying to depict, is if you look at the difference between where the actual curve is and where the approximated solution is, that right there tells you something about the accumulated error. So that's the error of approximation. And so we look at that and we think, oh, that's not very good. That seems to be a pretty big source of error, even though our curve seems to be going in a particular direction, kind of following a pattern, and our approximation is trying really hard to follow in that same direction too, even though our approximation is doing a decent job of kind of following the spirit of the solution curve, if not the exact location. So this error of approximation, we know, comes down to the step size. And so if you take a look at some other step sizes, you get a sense of what's going on. So the step size that we just saw, or we just used, was this step size of h equals 1, and that was us taking 3 steps, each one 1 unit in the x direction, in order to get to our approximated location. Now, if you wanted to, you could use a smaller step size. So what would it be if you used a step size of 0.2? That's the same thing as 1/5, right? So that means for every 1 unit in this horizontal direction, we're actually doing, if you count them, 1, 2, 3, 4, there's a 5th step there in order to get out there. So we're doing 5 steps, and that means in order to go 3 units, that would mean a total of 15 steps, which means a total of 15 calculations. Now, you remember how tedious it was to do even one of these calculations. And by the time you get done with 15 of them, you'd be pretty sick of it. Well, if you think that that's not that terribly accurate, this process right here gets you a curve that's still pretty close to the exact solution, but it's not dead on. That solution right there at a step size of 1/5 gets you closer to the right answer. But if you want to get even closer to the right answer, see the curve that's just underneath there, that's with a step size of 0.05, which is 1/20th, which means a total of 60 steps in order to go the 3 units, 1, 2, 3, in order to get out to here. And you can see that that approximation right there is really, really darn close to the exact solution. Now, you might be thinking, well, that's a price you'd have to pay, 60 calculations in order to get a pretty exact or pretty accurate solution curve. Now, just remember that that's 60 steps of tiny little line segments connected together, and it's going to do a better job of approximating our curve. So you might ask the question, why bother doing this, large steps? Why bother doing a small number of steps? Why not just use really, really, really small steps in order to get to where you want to go? And it turns out there's 2 main reasons. The first one's going to seem pretty obvious to you, but the second one might be a little less so. So the first reason is more calculations. More problems. Or more time. It turns out that in order to do calculations, it takes time. I know this is going to blow your mind, but it's not just true for humans, it's also true for computers. Since we're going in the direction of having a computer or a calculator do this for us, let's just imagine, for example, that we wanted to take a look at a situation where we have a fixed step size. And so if you had a step size of something like, I don't know, 0.1, 1/10, then if you stick that in your calculator or your computer and you find out that it takes time for the calculations, and let's say it takes exactly 1 second for calculations. Now, presuming that you're going to use the exact same computer to do different step sizes, we can do a quick comparison because this is a direct relationship between these two. So I want you to imagine a step size of 0.001, literally 100th of the step size. Well, 100th of a step size means it's going to take 100 times more. Literally, it's going to take 1.8 minutes to do that calculation. Now, this is doing the exact same approximation, going the same distance, but chopping it up into many smaller calculations. So, I don't know if you've ever waited 1.8 minutes for your computer to do anything, but I get bored after a second or two waiting for a web page to load. So this would be just interminable. But let's say you want to go really ridiculous and you reduce your step size to the point where you're talking about a trillionth of a unit, just a tiny little fraction. Well, it turns out this wouldn't take minutes, this wouldn't take hours, this wouldn't even take days, this would take 3,000 years. Yeah, I know, it's crazy. That same distance, if you split it up into step sizes of a trillionth of a unit, whereas 1/10 of a unit would take you 1 second, the much smaller step sizes can take much longer. So when we say more calculations means more time, we're not kidding. And even the fastest computers can get bogged down in these huge number of calculations. So just because we can do small step sizes doesn't mean that we want to wait around for it. So that's the first interesting reason behind why we don't just use super small step sizes. The second reason is a little bit different. This one basically is all about rounding error. Now, when I say rounding error, I mean how many decimal places are you going to round to, right? How many decimal places? And how many decimal places do you round each step, right? Because when you calculate each step, you have to do some rounding. And of course, how many decimal places do you round each step tells you how much information you have left to compute with. And of course, how many decimal places? Oh, I don't have to rewrite that whole thing. I'm just going to say, how many decimal places do you round your final answer? If you're going to round to 3 decimal places, then your step sizes are certainly limited, right? Because if your step size is 0.1, then rounding your answer to 3 decimal places, that's pretty close to your step size. But if your step size is 0.001, then you're already at your rounding limit. So the step size determines how many decimal places you're going to round your final answer, right? So this rounding error becomes super important. Super important. So the last little bit for this video, we're going to take a look at Euler's method as a formal program, as a formal algorithm. And so the couple of things that you need to recognize about Euler's method, in order to do it, you have to have 2 things. You have to have a differential equation, and you have to have an initial condition. That means you must have an initial value problem. what we're calling an IVP, to use Euler's method. You can't tell Maple to approximate a solution curve if you don't give it a starting point, right? Maple's going to look at you and go, well, I don't know what to do with that. It's just a differential equation. You have to tell me where you want to begin in order to draw the solution curve, in order to approximate it. So we're going to come up with the formalized logic behind this computer program. And it basically works kind of like a sequence that you might have seen in Calc 2. It says you want to know where your new independent variable value is. Well, you take your initial or your former independent variable value and you add your step size. Right? On our previous example, it was x, wherever we started before, the x coordinate plus our step size of 1, right? And you can do the same thing in the y direction. So it's y with a little subscript of k plus 1. And that's equal to wherever you were to begin with, plus some extra stuff. And the extra stuff here isn't just h. It's h times the slope, which is given by your function value, right? And that function value, that is the differential equation, right? So just a reminder of what we're dealing with here. The h value in this equations, that's our step size. And the step size is always in the independent variable direction. And the other piece of information that's super critical for this is this guy right here. And that's the slope value at the previous location. You want to know what the new location is? Well, you take your previous location y value, and then you add this thing right here, the slope times the step size. This gives you how far you're going up or down in the y direction. Right? And so all of this together forms the Euler's method, the formalized algorithmic program, right? And it's basically following a program like it's a computer program. Euler wrote this prior to anyone having a computer. You know, that word would have meant nothing to them in a mechanical sense. It would have just meant a person doing computing. But for us, this is something that we can program. You can actually make a spreadsheet that does Euler's method, right? Because it's recursive. But we're going to have Maple do it. And basically it boils down to, from a known point, that's our initial condition, if you remember. From a known point, our initial condition, establish the correct direction of the solution. And the direction, that's from the dE, from the differential equation. It tells you which way to go. Take a uniform step size, that's h, to reach the next location. Recalculate the line segment slope, right? That's the dE at the new location. And then repeat the process. Take a uniform step to reach the new location. And in the end, you wind up with a bunch of little line segments that connect to form an approximation of the true solution curve. And that's what we call the curve. It's not much of a curve, all those line segments, but that's the approximation of the solution curve. And so the last little bit on this page just reminds you, be systematic, right? This is a program. This is a computer program. So try to be as algorithmic and systematic as possible. And that's the best way to catch your mistakes. That means write things out, label things, fill in tables, read the tables that Maple gives you carefully and slowly to make sure that you're doing it right. And so that ends the video. And in the next video, we'll take a look at an example that we'll do on Maple.